Welcome. What we are covering today is not an incremental improvement to language model. It is a structural change in how AI systems reason, act, and improve. Traditional LLMs are passive sequence predictors. They take a prompt in and produce tokens out, with zero capacity to act on the world, remember what happened in the last session, or improve from their own mistakes. Agentic reasoning fundamentally breaks this mold. We position reasoning not as a byproduct of text generation, but as an organizing principle connecting perception, planning, decision making, and self-correction across time. To understand where we are in 2026, it helps to trace the evolutionary arc of AI deployment. Level 1 was just pure prompt engineering. Highly commoditized, no state, no action, just text in, text out. The entire competitive mode was which prompt template you wrote. Then level 2 introduced context awareness, streaming documents into the context window, adding RAG pipeline, making the model at least aware of the relevant data, even if it could not act on it persistently. Level 3 next introduced explicit reasoning traces. System 2 thinking made auditable, chain of thought, tree of thought, react. These are level 3 systems that externalize reasoning so you can inspect, score, and verify it before committing to an action. And this is the last level that most enterprises have actually deployed in production at scale today. The competitive frontier in 2026 is level 4, Agentic AI. Systems that autonomously decompose long horizon goals into directed graphs of executable subtasks, invoke tools to act on the world, and operate without a human in the loop for every decision. Next, highly regulated industries such as finance, healthcare, defense are pushing towards level 5, governed agentic AI, where every action is wrapped in zero trust verification, cryptographic audit trails, and mathematical behavioral contracts before execution. Then we have level 6, which is ecosystem intelligence, agents that interface directly with the physical world, managing urban infrastructure, regulating biological systems, coordinating planetary scale logistics. We are already seeing early deployments of level 5 and the first research prototypes of level 6. The question is not if we'll get there, it is how safely. So why did we have to evolve past the traditional LLM? It is because the static pre-training creates a fundamental reality gap. A model trained on a fixed snapshot of the internet operates with the equivalent of operational amnesia. It cannot track what actions it has already taken, does not know the current state of environment, and resets completely at the end of every session. This works for isolated singleton tasks, but it fails catastrophically for any workflow where state matters. Debugging a codebase across multiple sessions, or managing a customer relationship over weeks, or coordinating a multi-step scientific experiment. The passive predictor cannot navigate the multi-step branching workflows where the environment itself changes mid-flight. And every real-world enterprise task is exactly that kind of workflow. All of agentic reasoning is organized into 3 complementary layers that will trace through the rest of this talk. The first layer is foundational agentic reasoning, the bedrock capabilities of a single agent, planning, tool use, and search in stable environments. The second is self-evolving agentic reasoning, how agents improve through feedback, memory, and continual adaptation across episodes. The third is collective multi-agent reasoning, how multiple specialized agents coordinate, communicate, and share knowledge to exceed what any single agent can do. Critically, all three layers are analyzed through two optimization lenses. In-context reasoning, which scales inference time compute without touching the model parameters, and post-training reasoning, which internalizes strategies into model weights via reinforcement learning. And this taxonomy is not just academic, it is actionable design checklist for building production-grade agentic systems. The paradigm shift here is both technical and economic. The traditional scaling hypothesis said, train a bigger model and get better performance. The agentic shift says something different. Instead of betting everything on pre-trained compute, you scale what happens at inference time. Rather than relying solely on parameters frozen months ago, agents search, verify, retrieve, call tools, and loop through reasoning chains before finalizing a response. This is called test time interaction, and it unlocks a fundamentally different kind of intelligence. A frozen LLM model asked a hard multi-step question will give you one answer. But when a React agent using the same model will search, verify, backtrack, and refine, then it will often land on the correct answer that the vanilla model would have missed. So the intelligence is not in the weights, rather it is in the interaction loop. To achieve meaningful long horizon capability, agents are inherently stateful. They bypass the context window's hard ceiling through deep integration with external vector databases, knowledge graphs, and structured memory stores. The context window of even the largest model resets at the session boundary, but an agent's memory does not. This is the difference between a tool that you use and a system that knows you, your preferences, your history, the state of your ongoing projects. Hence, statefulness is not an optional enhancement. It is an architectural prerequisite for any agent that operates across more than one interaction. Without it, every task restarts from zero, and the value accumulated from previous work just evaporates. Mathematically, the agentic reasoning acts as a partially observable Markov decision process, or POMDP. The agent observes a partial view of the environment. It does not see the full state and must reason about which action to take next. The key innovation is the introduction of a reasoning trace space between observation and action. At each time step, the agent first generates an internal thought, a reasoning chain, a plan, a critic, and then converts that into an external action. This decomposition formalizes think before you act structure that distinguishes agentic system from reactive ones. It also gives us a precise target for optimization, either through a better prompting at the inference time or through reinforcement learning during the post-training. Early in-context agentic methods such as React and Tree of Thought treat the reasoning trace space as a search landscape to be explored at the inference time, without ever touching the model's parameters. React interleaves reasoning thoughts with explicit tool calling actions in a dynamic loop. Think, act, observe, and repeat. Tree of Thoughts extends this by treating partial thoughts as nodes in an explicit search tree to find optimal reasoning path. These methods are powerful precisely because they are modular. You can apply them on top of any frozen LLM without retraining. But their performance is bounded by model's existing knowledge and the quality of the search heuristics. Modern reasoning models go further and optimize the parameters themselves, specifically for long horizon reasoning. DeepSeek R1 and O series models are trained using reinforcement learning, such as variants of GRPO, to internalize reasoning strategies that emerged at the inference time. The result? We have models that do not just generate text but reason deliberately, verify their own output, and backtrack, all automatically without explicit prompting to do so. When we connect multiple agentic systems, we shift from single POMDP to a decentralized POMDP. In this formulation, each agent has its own partial observation and its own reasoning policy. But the agents must also coordinate to achieve a shared global objective. In multi-agent system, communication between agents is not merely a signal transmission, because one agent's external action can serve as a prompt that triggers another agent's internal reasoning chain. AutoGen, Camel, MetaGPT, and QAI are all frameworks that operationalize this, assigning distinct role and coordinating through natural language message passing. The challenging open question is not how to build the agents, it is how to design the communication topology and incentive structure so that decentralized reasoning processes converge on coherent global behavior. Self-evolving agents add a second optimization loop above the task loop, a meta update that improves the agent system itself across episodes, not just within them. The self-evolution is categorized into three types. Verbal evolution, which updates reflections and textual guidelines. Reflection is the canonical example of this, synthesizing error logs into self-critique that conditions future reasoning. Next is procedural evolution, which expands the agent's action space by writing new executable tools or skills, such as Voyager does this in Minecraft. And finally, we have structural evolution, which rewrites agents' own architecture or code. For example, Alpha Evolve treats the agent's source code as a hypothesis space and uses an LLM as a mutation operator. So this framework unifies diverse self-improvement approaches under a single principled update rule. Every autonomous agent rests on three bedrock capabilities. First is planning, that is the ability to decompose abstract goals into directed acyclic graphs of concrete executable subtasks. Next, we have tool use, the ability to invoke external modules such as APIs, code interpreters, web browsers, databases to act on and gather information from the world. And finally, we have search, the ability to actively query information sources, evaluate the retrieved evidence, reformulate queries, and iterate until the agent is satisfied. These three are not independent, they are deeply intertwined, such as effective planning requires knowing which tools are available and what information is accessible. Effective tool use requires a planning context that knows when to invoke and how to compose. An effective search requires both planning to guide the search strategy and tool use to execute the query. Hence, foundation and interdependence. That is the key takeaway here. Planning for LLM agents may include anything from workflow design to tree search to process formalization. At its core, planning requires breaking a complex directive, such as build a production ready REST API for our authentication service, into a directed graph of executable subtasks, such as first design a schema, write the endpoints, generate the tests, validate against the specs, deploy to staging. So we have methods like Revu, which explicitly decouple the planning phase from the execution phase. The agents generate the plan first and then execute it, rather than interleaving thinking and acting. Then we have hierarchical approaches like STP, which use hypertrees to represent multi-level plan with cross-level dependencies, enabling both fine-grained and coarse execution granularity. The key design tension that we have is that if we decompose too finely, we get planning overhead that slows the agent. And if we decompose too coarsely, then we get compounding errors when a high level step fails. A critical industry shift we notice, prompt engineering is dead as a primary production paradigm, and welcome to flow engineering. So where prompt engineering tuned the text you sent to the model, flow engineering designs the deterministic controls that governs when and how the model is invoked. Developers now hard-code rigid state machines, state transitions, and checkpointing logic, using the LLM only for specific cognitive decisions at well-defined nodes, rather than letting it generate chaotically. The LLM is treated as a precisely invoked reasoning component within a larger deterministic workflow, not as a controller of the workflow itself. This shift dramatically reduces compounding errors. When you control a flow, the failure at one node triggers a defined error handling path, not an uncontrolled hallucination cascade. Flow engineering is also auditable by design. Every state transition is logged, every tool call is recorded, and every branch is reproducible. Flow engineering relies on a toolkit of mature design patterns that have emerged from production experience. We have reflection pattern where the agent first produces output and a separate critic evaluates it. And then the agent revises. It is useful for code generation and document drafting where quality is verifiable. Then we have tool use where agent generates a structured tool call, receives a structured response, and integrates it into reasoning trace. In planning, the agent explicitly reasons about its multi-step plan before taking any tool action. We have orchestrator worker, where a high-level orchestrator agent decomposes tasks and delegates subtasks to specialized worker agents, each with a focused context. Then we have evaluator optimizer pattern, where a dedicated evaluator agent scores the output of worker agent and provides structured feedback that the optimizer uses to improve. Each pattern is a reusable building block, and sophisticated production systems will combine multiple patterns into hybrid architectures tailored to their own domain. Tool use is the mechanism by which agents escape the closed world of pure text generation and act on external reality. In production systems, free text parsing of tool calls is forbidden. It is a reliability catastrophe. Every tool invocation must return a structured JSON object that exactly matches a declared schema. Because downstream systems depend on machine readable outputs, not human interpretable proofs. This is called JSON imperative. Agents are not just language models, they are interface clients with strict API contracts. The tool use approaches are organized into three tiers: in context integration, such as React, which are training free and use prompting. Then we have post training integration, such as Tool Former or Tool RL, which are learned during training. And finally, we have orchestration based integration, such as Hugging GPT or Octotools. These are system level coordination across multiple tools. So the progression from in context to post training and finally to orchestration reflects production maturity. When an enterprise agent has 50 plus available tools, injecting all their schema description into the context is counterproductive. It will dilute model's attention and degrade recall quality. The solution is retrieval-augmented tool selection. First, embed tool description as dense vector, build a semantic index, and at inference time, retrieve only 5 to 10 most relevant tool schemas for the given task. So this mirrors how enterprise developers work. We don't memorize every API in our organization. Rather, we search our developer portal when we need something specific. Gear framework implements this efficiently by delegating tool selection to a lightweight model and hence reserving the expensive large model only for final reasoning and execution step. Traditional RAG is a passive, single shot lookup. Query arrives, retrieve top K chunks, stuff them in the context, and generate. Agentic RAG, on the other hand, transforms this into an active iterative process. Agent queries, evaluates the retrieved evidence for sufficiency, reformulates its query if the evidence is incomplete or contradictory, and continues searching until it has high confidence in the answer. This is adversarial interrogation of the knowledge base, not passive consultation. Web search agents using Agentic RAG use sequential decision process. Do I have enough answer? If not, should I broaden my search horizontally across multiple sources or drill deeper vertically into any specific domain? We have benchmarks like DeepSeek, which test this iterative search capability with a non-curated, dynamically changing web answers, where any passive RAG would simply fail. Unimodal web exploration is modeled as a sequential decision matrix with an explicit exploration trade-off. At each step, agent decides, do I stay on this domain, extract more depth, scanning deeper into the current page structure, or do I broaden horizontally and check alternative sources? So WebWalker evaluates structured website traversal where agent must navigate coordinated horizontal and vertical exploration. Mind2Web benchmarks long horizon browsing with citation grounded synthesis. The agent must not only find the answer, but cite the specific evidence. The challenge is compounding context. As multi hop browsing continues, context fills with partially relevant intermediate observations. An agent must actively manage what to keep and what to discard. The same memory problem that we see inside the agentic planning loops. We now rely heavily on multimodal reasoning agents that can parse not just text but rendered web interfaces, images, charts, and videos. Visual intelligence allows agents to interact with complex UI elements, such as CAPTCHA protected forms, rendered JavaScripts, visual dashboards, that pure HTML scrapers and text only models cannot comprehend. Visual Web Arena extends Web Arena with visual rendering, requiring agents to align instructions with actual rendered UI components rather than raw HTML. Browsecomp specifically enforces mandatory image dependence to prevent text-only shortcuts, ensuring that visual evidence is genuinely incorporated into the reasoning. Paper Arena requires agents to coordinate PDF parsing, figure understanding, and web search simultaneously to answer research level questions. The frontier is temporal video reasoning, where agents must extract reason over visual temporal evidence from video streams in real time. Planning, tool use, and search do not operate sequentially. They compose into continuous perception action loop that is fundamental runtime of an autonomous agent. The agent perceives its environment, engages its reasoning trace to plan the next action, executes an external action via tool or search, receives the result as a new observation, and updates its plan accordingly. This loop runs continuously, not just once per query, but potentially hundreds of times within a single complex task. The critical property is that every stage informs every other stage. So search will modify the plan, tool call failure will trigger replanning, new observations update agent's world model, and breaking the loop at any stage, such as caching observations or short circuiting tool calls, ignoring feedback, that will degrade the coherence of the entire system. Despite the power of foundational single agent systems, they face three hard failure modes. First, compounding early errors. A miscategorization in step 2 of a 20-step plan propagates and amplifies through subsequent steps, resulting in a catastrophically wrong final answer, even if every later step is locally correct. Second, context drift. As a long running agent accumulates observations, tools output, and intermediate results, the context forms context pollution, noise that actively harms the quality of reasoning for current subtasks. And the third is recursive loops. Agents can get stuck solving the same subproblem repeatedly, unable to recognize they are in a loop because their working memory does not track task level state. These failure modes motivate the evolution layer, the next part of the taxonomy. To summarize part 3, we have built an autonomous problem solver. Given a complex goal, a single foundational agent can decompose it into plan, invoke tools to act on the world, search for missing information, and iterate through a perception action loop until it reaches an answer. This is already enormously powerful. Gaia benchmark performance has crossed 90% for well engineered single agent systems on general reasoning tasks. But single agents are brittle. They accumulate error over long tasks, pollute their own context, and cannot learn across session. The architecture is complete for a single episode. What we need next is the ability to improve across episodes. That requires evolution, feedback mechanisms, memory systems, and continual adaptation. That is part 4. Self evolving agentic reasoning marks the transition from static program that is correct but frozen to an adaptive intelligence that improves through experience. The meta update equation captures this precisely. After each episode, the agent's evolvable system state, its memories, skills, guidelines, or even architectures, is updated using the trajectory and the feedback. This is a non parametric path to continual learning. The agent accumulates operational wisdom purely through experience without retraining the base model. Agents with rich self-evolution mechanisms consistently outperform agents using identical base model but with no evolution, demonstrating that the adaptation infrastructure around the model, not just the model itself, is the primary determinant of performance. Feedback is the lifeblood of self-evolution. Without evaluative signals, the agent has no mechanism to determine what to keep, what to revise, and what to discard. The feedback is categorized into three types. Environmental feedback that comes directly from the execution environment. These are things like compiler errors, test failures, web page rendering results, API response codes, etc. And this is the richest and most objective signal because this is the ground truth. The environment does not lie. Next comes internal feedback, which is generated by the agent itself through self-critique. The agent evaluates its own output against its own standards, identifies inconsistencies, and generates self-correction signals. And finally, we have human feedback, which is most aligned but most expensive, requiring human effort for every label signal and thus limiting scalability. Sophisticated system would combine all three: environment feedback for objective grounding, internal critique for immediate correction, and periodic human feedback to calibrate the overall direction. Intra-test time adaptation means improving reasoning within a single task episode, adapting on the fly, not across the session. Reflection is a canonical system. The agent publicly reflects on its own failures using environmental feedback, synthesizes a verbal self critique, and stores that critique as short term memory that conditions the next reasoning attempt. The innovation is that verbal reflection is stored explicitly. It is inspectable, auditable, and transferable, rather than being silently absorbed by gradient descent. DeepSeek's mind map pushes this further. Specialized mind map subagents pause the main generation loop to cluster and graph structure the accumulated context, preventing the primary model from losing its logical thread during heavy tool use. Think of it as dedicated context management running alongside the main agent, continuously organizing the scratchpad. DeepSeek R1's approach to self-evolving reasoning is notable because it internalizes the structuring capability into post-training rather than relying on explicit prompted scaffolding. The model learns through reinforcement learning on large-scale reasoning tasks to autonomously generate structured reasoning traces that organize complex multi-step thinking into coherent chains without losing context. The mind map concept takes this further. Rather than treating the reasoning trace as a flat text, dedicated agents restructure the in-context reasoning into a dynamic knowledge graph, making the semantic relationships between concepts explicit and navigable. This prevents a known failure mode in long context reasoning where model forgets its own earlier conclusions because they are buried under many subsequent tokens. Structured context is a form of cognitive scaffolding. It externalizes working memory organization. To learn permanently across sessions, not just within an episode, agents require diverse, multi-tiered memory systems. Token level memory stores information as explicit inspectable text, JSON, or knowledge graph triples. These are the most transparent and iterable form. Next, we have parametric memory, which encodes information directly inside models through fine tuning or model editing. These are fastest at the retrieval with zero latency, but opaque and expensive to update. And finally, we have latent memory that stores information in continuous hidden states, KV caches, and compressed embeddings. These have high density and are efficient, but not human readable. Most production memory system would mix all three. Token level for facts that need to be audited or deleted, parametric for deeply internalized domain skills, and latent for compressed working context. The art is routing the right type of information to right memory tier. Episodic memory is the most direct form of experiential learning. Store the complete trajectory of past track episodes, the sequence of observations, reasoning traces, tool calls, and outcomes, and then retrieve relevant past traces to inform current decisions. Reflection, for example, stores both the interaction trajectory, and self-generated verbal critique as long-term episodic memory that the agent can explicitly recall. Jarvis 1, on the other hand, stores successful Minecraft survival experiences as plan environment pairs and retrieves the most relevant match when facing a novel situation. The strength of episodic memory is high informational fidelity. The agent can literally replay a past solution. But the weakness is poor generalization. Raw trajectories from one specific context often do not transfer cleanly to novel contexts with slightly different parameters. This further motivates to the next layer, abstracting principles from episodes rather than just replaying them verbatim. To overcome the generalization limit of raw episode replay, strategy-based memory distills transferable abstractions from accumulated trajectories. Procedural memory, as seen in Voyager, extracts verified reusable skills from successful execution traces and permanently adds them to agents' tool library and action spaces. Once a skill is learned, it can be invoked as a single step in future plans, thus dramatically compressing the planning horizon for familiar subproblems. Buffer of thoughts maintain a meta buffer of thought templates, generalizable cognitive skeletons that can be instantiated for new problems without re-deriving the approach from scratch. Agent workflow memory extracts reusable navigation patterns from web interaction histories, enabling zero-shot generalization to pages the agent has never seen but that follow similar structural patterns. These abstracted patterns represent the difference between raw experience and genuine expertise. Intertest time evolution takes the time horizon of adaptation from within episode to across episode to across tasks and finally to across lifetime. Rather than adapting on single tasks, the agent accumulates capabilities progressively across diverse task types and domains, building a compounding knowledge base that makes each new task easier than the last. EvoSC automates this by continuously distilling verbose textual trajectories into compact parametric soft embedding, converting episodic experiences into intrinsic intuitions that is woven into model itself. Memory R1 applies reinforcement learning to train extraction module itself, learning which experiences are worth retaining and which can be discarded. The result is that the agent is not just accumulating memory passively, it learns how to learn, improving the quality of its own memory as it operates. Memory, unlike human cognition, does not have a biological forgetting curve built in. Without active management, agent memory grows without bound, accumulates contradictions, and suffers from staleness. Outdated facts that were once correct, silently corrupting future reasoning. DSmart encodes facts as knowledge graph entries and triggers update operations the moment contradictions are detected. JEP implements temporal soft delete. Rather than hard deleting outdated facts, it marks them with invalid timestamp, preserving historical context while ensuring current queries return accurate current answers. FadeMem implements adaptive exponential decay inspired by Ebbinghaus forgetting curve, memory entry decay based on elapsed time and access frequency, with high value entries promoted to permanent storage. Thus, it retains critical fact at lower cost. Hence, forgetting is not loss, it is compression towards relevance. The central insight of this part is that evolution solves the brittleness that limits foundational single agents. A foundational agent plateaus at its initial knowledge state. Its ceiling is the context window and models pre-training. On the other hand, an evolving agent ceiling is replaced by trajectory, compounding improvement through accumulated experience, abstracted skills, and self-refined memory. But evolution still operates on a single agent's experience. The next natural step is that what if multiple agents could share their learning, parallelize the accumulation of experience, and collectively surpass the capability of any individual agent, no matter how evolved? That is multi-agent layer. The teams do not just divide the work, they amplify intelligence. Distributing reasoning tasks across multiple specialized agents dramatically lowers error rates on complex workflows compared to using a single massive model for everything. Just as human organizations outperform individuals on complex tasks by assigning specialized roles to domain experts, multi-agent systems assign specialized roles, planner, executor, critic, verifier, to agents optimized for each function. MetaGPT models this as a software engineering team. A product manager writes the spec, architects design the system, engineers implement it, QA agents test it, a project manager coordinates the whole workflow. Thus, each agent operates with a focused context matched to its role, avoiding the context pollution that plagues general purpose single agent. Thus, the collective system exhibits capabilities that no individual component possesses. Modern agentic platform implements true swarms in which a team lead agent autonomously spawns specialized worker delegates without a human designing the team composition. Anthropic's Cloud Code implements this with agent teams configuration. One team lead interprets the project goal and dynamically assigns distinct roles: front-end engineer, back-end engineer, QA testers, two specialized teammate agents. Each teammate operates in a Git work tree isolated directory branch to prevent race conditions and merge conflicts at the file system level. Critically, the teammates communicate directly with each other through an internal mailbox section, enabling adversarial debugging and hypothesis challenges without constant routing through the human operator. Quality control is maintained via a programmable hooks like teammate idle and task completed, which halt completion if predefined tests fail. Developers monitor the parallel execution through the split plane terminal, watching multiple agents stream simultaneously, a generally new modality of software development oversight. Swarms are not generic, they are deeply customized by domains. A software engineering swarm typically includes architects who design system interfaces, developers who implement specific modules, QA engineers who write and execute tests, security reviewers who audit for vulnerabilities, and a project manager who coordinates dependencies and timelines. Similarly, a financial analysis swarm includes research analysts who gather market data, risk assessment agents who model downside scenarios, compliance agent who verify regulatory constraints, and a portfolio manager who synthesizes recommendations. The key insight is that while a generic agent achieves mediocre performance across domains, domain specialized swarms with role appropriate agent achieve state of the art performance in their specific vertical. Specialization is not just about what agent knows, it's about what context it operates with and what tools it has access to. Multi agent collaboration is organized along two axes. In context collaboration, where agents coordinate through natural language at inference time without parameter updates, and then we have post-training coordination, in which agents are trained via RL to optimize collaborative behavior as a joint policy. Within in-context collaboration, we have further two subvariants. First, we have manually crafted pipelines with fixed handoff protocols. Agents operate on predetermined sequences, and each agent receives a defined subset of context. And then we have LLM driven dynamic dispatch, where an orchestrator agent decides in real time which worker to delegate each subtask to, based on semantic understanding of task requirement and agent capabilities. Post training coordination basically treats collaboration itself as a trainable skill, rewarding agents for group outcomes rather than individual outputs, suppressing individual hallucinations, and misaligned subgoal pursuits. In context, multi agent collaboration operates entirely at the prompt level. No retraining is required, making it the dominant paradigm for rapid deployment. The collaboration functions as natural language handoff. One agent completes a step, writes its output as structured message, and the next agent in the pipeline receives that message as a part of its context. This mirrors human team communication. A Slack message from one colleague triggers the next action in another. AutoGen, Camel, and LangGraph all implement variation of this pattern. The engineering challenge is routing. Which agent receives which message with which subset of the accumulated context? Dynamic LLM driven dispatch solves this by using a dedicated orchestrator model to make routing decisions, enabling adaptive team compositions that respond to surprising task requirement rather than following a rigid predetermined sequence. The design of the communication topology, who can talk to whom, is as critical to systems performance as the design of individual agents. Full connectivity, where every agent talks to every other agent, generates enormous amount of token overheads and introduces conformity bias. Agents start to agree with the consensus even when their individual reasoning says something different. Sparse graph, where agents only communicate with their direct task dependencies, minimize bandwidth and reduce sycophancy. GPT Swarm treats the communication graph as a differentiable architecture and trains it end to end, automatically pruning unproductive communication edges and strengthening productive ones. The optimal topology depends on the task structure. Hierarchical tasks favor tree topology, collaborative debate tasks favor small, fully connected groups, pipeline tasks favor directed acyclic graphs. Hence, topology is a first class design decision and not a default. Post-training collaboration goes beyond prompt-based handoffs to actually train agents to optimize collaborative behavior as a joint policy. Systems trained with multi-agent RL reward agents for group outcomes. The whole team succeeds or the whole team fails. And individual rewards are derived from the collective results. This suppresses two severe failure modes in the native multi-agent systems. Individual hallucinations, where one agent generates a confident wrong answer that then poisons the rest of the system. And compute hoarding, where agents grab more context than they need, crowding out collaborators. MAPO-RL and other multi-agent RL systems demonstrate that training for group relative reward yields dramatically more coherent collective behavior than training agents independently and then composing them. The agents learn complementary strategies, not just how to perform their role, but how to adjust their behavior based on what their collaborators are doing. A multi-agent system requires a careful memory architecture that balances private agent scratchpads with a shared organizational knowledge base. There are three topological choices. Local memory, where each agent maintains fully private isolated state with coordination through explicit message passing. This eliminates contention and maximizes autonomy, but at the same time accumulates redundancy as multiple agents independently solving the same subproblem without sharing solutions with each other. Next, we have shared memory, in which a centralized pool is used that all agents read from and write to, with coordinated access control. It has zero redundancy but high concurrency complexity and serious risks of write conflicts, stale reads, and memory poisoning from one bad agent contaminating the pool. Then we have hybrid, where fast local caches are there for working memory and a governed central repository for verified long-term knowledge, mirroring CPU cache architecture. The adaptive memory framework adds a dedicated refresher agent that continuously audits shared pool, purging obsolete entries and resolving inconsistencies in a background maintenance loop. Here is where things get fascinating and counterintuitive. Multi-agent systems exhibit sociological behaviors that mirror human group dynamics. And some of those behaviors are actively harmful to reasoning quality. Current research confirms that LLM agents obey social impact theory. Agents are more likely to change their stated answer when opposed by many agents, by agents presented as having high authority or expertise, or by agents operating in close communication proximity. This is not a software bug. It is an emergent social property arising out of the fact that agents are trained on human text, where social consensus following is often the correct behavior. But in a reasoning context, social compliance is catastrophically wrong. The goal is to find the correct answer, not the most popular one. Understanding swarm psychology is prerequisite to designing collaborative systems that maintain intellectual independence. Even highly accurate individual agents can succumb to conformity bias when placed in a multi-agent setting. This has been empirically demonstrated. Take an agent that gets 95% accuracy in isolation, place it in a group where majority gives the wrong answer, and the agent's stated answer flips to match the majority, even overriding its own correct internal reasoning trace. This is artificial peer pressure at scale, and it represents a fundamental reliability hazard for multi-agent system tasked with high-stakes decisions. Mitigation strategies include explicit debate frameworks that require agents to commit to and defend their individual answer before seeing what the group thinks. Majority report protocols that specifically weight answers that dissent from the majority, and independent verification agents whose role is specifically to challenge consensus answers rather than confirm them. Beyond conformity bias, multi-agent systems face echo chambers, with agents reinforcing each other's errors rather than correcting them. Psychophancy, with agents generating outputs designed to please the orchestrator rather than to be accurate, and communication overhead that can become the dominant cost in large firms. The token budget consumed by inter-agent messaging alone can exceed what agent spends on actual reasoning, at which point we have built an expensive coordination system that barely reasons. These sociological bugs increase monotonically with system size, suggesting that the naively scaling the number of agents is not the path to better performance. The solution is architectural. Sparse communication graphs, independent reasoning commitments before group deliberation, explicit devil's advocate roles, and RL training that rewards accuracy over consensus. Despite the sociological challenges, swarms remain the most powerful reasoning architecture available for genuinely complex open ended workflows. Tasks that require simultaneously managing large code bases, integrating domain expertise from multiple fields, performing parallel independent analysis, and synthesizing contradictory evidence cannot be effectively handled by any single agent, no matter how capable its base model is. The benchmarks confirm it. Multi-agent systems consistently outperform the single best baselines on software engineering, scientific discovery, and enterprise workflow tasks. The challenge is not the capability, it is reliability, cost, and governance. And this is what the next part addresses. Deploying agentic swarm at scale breaks every assumption that traditional software architecture was built on. Legacy infrastructure was designed for deterministic microservices with predictable request response cycles, fixed throughput profiles, and circuit breaker patterns designed for well understood failure modes. An agentic workflow is non deterministic. A single user request may fan out into 50 unpredictable subtasks with variable depth, variable duration, and variable resource consumption. Hence, circuit breakers tuned for millisecond API latency cannot accommodate an agent that might spend 45 seconds doing multi step web search. Retry policies designed for REST calls cannot handle agents that perform real world side effects, such as sending emails, modifying databases, executing codes that cannot be safely retried. The infrastructure must be rethought from the very first principles. Contemporary agentic backends decouple the reasoning layer from the execution layer entirely. The system continuously perceives events, a user message, a tool response, an error condition, routes the semantic payload to the appropriate spatialized reasoning model based on latency requirement and task type. executes the resulting plan via tool invocation and API calls, collects results, and loops back. The routing layer treats reasoning as a shared service accessed by multiple concurrent agent processes. Different agents running simultaneously on different tasks all share reasoning capacity from the same pool of models. This is comparable to how databases handle concurrent transactions. The computation is shared, but contexts are isolated. The modular design also enables incremental rollout. You can upgrade the planning model without changing the execution layer, and vice versa. If every enterprise builds heavily siloed proprietary agent systems, we trigger an interoperability crisis that mirrors the pre-USB era of consumer electronics, where every device had its own proprietary connector. An Anthropic agent and an OpenAI agent cannot natively discover, authenticate, or delegate to each other, creating liability chains and audit gaps in any cross-organizational workflow. A procurement agent from company A needs to interact with supplier inventory agent from company B, but they cannot communicate because they use incompatible protocols. This fragmentation actively destroys the value proposition of autonomous agents for multi-party workflow, which is precisely where the most enterprise value lives. The industry has recognized this problem and has responded with open standards. The Model Context Protocol, or MCP, championed by Anthropic and now adopted broadly, is the USB-C for AI, a universal standard built on JSON RPC 2.0 that defines how agents discover and interact with tools, databases, and external resources via plug-and-play client-server architecture. An AI host application uses an MCP client to format requests into a standardized protocol, which queries an MCP server, which is a lightweight bridge connected to enterprise resources like GitHub, Slack, or SQL database that exposes its available tools and data schema dynamically. The 2026 Agentic Standard identifies three complementary open protocols together. First, we have MCP for agent to resource communication. Then we have A2A, or agent to agent, for agent to agent communication. And finally, we have Agent Communication Protocol, or ACP, as an overarching system-wide orchestration standard that ensures all internal agent messages, human AI interactions, and routing topology remain compatible across diverse applications. Together, these three form the complete architecture of Agentic Web, enabling plug-and-play interoperability at every level of the stack. The agent-to-agent, or A2A protocol, developed by Google and donated to Linux Foundation, is supported by major enterprise vendors including SAP, ServiceNow, and PayPal, and is built on standard web infrastructure, HTTPS, JSON RPC 2.0, and server-sent events for real-time streaming. The protocol follows a precise three-step lifecycle. Discovery: the client agent queries a registry for agent cards. Agent cards are JSON formatted digital resume advertising each remote agent's capabilities and security schemas. Next, we have authentication, which leverages OAuth 2.0 or OpenID Connect to cryptographically verify credentials. And finally, communication, where agents exchange tasks containing messages as structured text parts, file parts, or data parts. Because agentic tasks may span hours or days, A2A is deeply asynchronous, supporting webhook notifications and defined life cycles. Submitted, working, input required, completed, failed. So, together with MCP and ACP, this means an Anthropic agent running on AWS can discover, authenticate, and delegate to a specialized agent on Azure with complete audit trails and without month of custom integration work. Underneath the software stack, hardware is bifurcating sharply to match agentic workloads. Traditional GPU architectures like NVIDIA Blackwell series are optimized for massive parallel throughput, ideal for large independent batch inference, but incurring significant latency penalties for highly sequential branching tool calling loops that characterize agentic execution. The Samba Nova SN50 reconfigurable data flow unit is explicitly purpose-built for agentic AI. Its data flow architecture minimizes data movement during multi-step planning, claiming 5x maximum speed and 3x throughput versus NVIDIA B200 GPUs specifically on agentic inference patterns. Google's Ironwood TPU v7 integrates hardware-level optimizations for fast agentic feedback loops and uses optical circuit switches for ultra-flexible network topologies, delivering an estimated 30% reduction in total cost of ownership versus equivalent NVIDIA infrastructure for multi-agent workloads. Where agents interfere directly with physical reality, such as robotics, autonomous vehicles, industrial control, the compute moves to edge and safety requirements becomes hardware requirement. Ultra low power ML SoCs or machine learning system on chips enable real-time perception and planning at the endpoint, with inference latencies below 100 milliseconds required for closed loop physical control. The critical safety innovation is hardware level e-fences. Deterministic fail-safe circuits embedded directly in silicons that monitor agents' command outputs and physically override the system, cutting motor power, activating emergency brakes, triggering fail-safe mode. If the agent issues a command that exceeds predefined safety boundaries. These circuits bypass the AI completely. No matter what the agent decides, the hardware will never allow certain classes of dangerous actions to execute. Hence, physical safety is not a software guardrail. It is now a hardware guarantee. Non-human agentic identities are projected to exceed 45 billion globally by the end of 2026, outnumbering the human workforce 12 to 1, creating a governance crisis that no existing legal or software framework was designed to handle. This is the AI principal agent problem at civilizational scale. Profound information asymmetry, discretionary authority exercised at machine speed, and a digital actor that cannot be motivated by incentives or directly sanctioned by law. The industry response is agent behavioral contracts or ABCs, formal mathematical logic specifications that extend design by contract principles to multi-turn autonomous agents, establishing mathematical environments invariants that must hold true across extended sessions, enforcing governance constraints over physical and digital action, and providing a compositionality theorem that guarantees safety properties compose correctly over entire multi-agent interaction chain, meaning you can prove that a verified verifier agent combined with a verified reasoner agent produces a verified composite system, not merely hope that they are safe together. Architecturally, level 5 deployments enforce this by routing every proposed agent action through an independent verifier agent that cryptographically approves or rejects it before execution. Thus, autonomy and governance co-designed from first principle, not retrofitted as an afterthought. Traditional benchmarks measure single-turn accuracy. Ask a question, score the answer. But this completely fails to capture the failure modes of agentic system. Multi-turn reasoning induces cascading errors. A plausible sounding wrong decision in a third step of 15-step workflow can produce a confidently wrong final answer with no visual warning signs in the final output. Outcome metrics give no visibility into how the agent got there. Did the agent get the right answer through a correct reasoning path or through lucky error cancellation? You cannot improve what you cannot measure, and the field has been measuring the wrong things. The evaluation gap is the most critical open problem in agentic AI. Without rigorous multidimensional benchmarks, it is impossible to know whether a new technique is genuinely better or just gaming the outcome metric through a different failure mode. The correct unit of evaluation for an agentic system is the trajectory, the full sequence of observations, reasoning traces, tool calls, and intermediate results that led to the final answer. Trajectory metrics measure every branch point decision, every tool call, whether we have correct invocation or hallucinated schema, every retrieval, whether we have relevant result or semantic mismatch, and every self-correction event. For example, LLM as judge systems are now integrated directly into CI/CD pipelines. After every code commit, a judge LLM evaluates whether a sample of agent trajectories on a held out benchmark set degraded, improved, or remained stable. Test time scaling evaluation measures how agent accuracy changes as you give the system more inference time compute budget, more search, more iteration, more parallel trajectories, providing a scaling curve that characterizes the system's potential ceiling. The 2026 benchmark landscape shows capability saturation at the frontier and completely collapsed cost barrier. Gaia, testing real-world questions requiring reasoning, multimodality, and web browsing, has been crossed at 90% by GPT-5, effectively closing the benchmark. SWE Bench Verified, which is autonomous resolution of real GitHub software engineering issues requiring multi-file code changes, test execution, and iterative debugging, reaches 74% with Cloud 4.5 Sonnet, making autonomous pull request resolution a baseline expectation for engineering team. OS World, which is cross-application GUI navigation across diverse operating systems, sits at 62%, proving that desktop computer use is no longer a critical bottleneck. The cost barrier has also collapsed. DeepSeek architecture demonstrated a 94% cost reduction for accessing massive agentic reasoning compute, shifting the primary challenge entirely from can we afford to reason to can we integrate and governed safely. The next frontier benchmarks, such as SWT bench for autonomous test case generation, mid-browse comp, and FinAgent bench, are already harder, continuously tracking genuine difficulty rather than plateauing. Agents exhibit exceptional performance on mathematical reasoning and software engineering precisely because these domains have objective, executable ground truth that enables agentic self-verification. A code agent can run the generated code and observe whether the tests pass or fail. No human evaluation is required. This closes the feedback loop that makes self-evolving agents dramatically more effective in symbolic domains than in subjective ones. Vibe coding, that is generating substantial software from natural language specification, is now a production validated paradigm. With SWRL trained model demonstrating that RL optimized code editing policies generalize to previously unseen repository structure. The key enabler here is test time verification. Agents that can run, test, observe, and iterate on their outputs converge to correct solution at rates far exceeding non-agentic models. The emergence of AI scientist agent that are fully autonomous systems that execute the complete scientific research cycle, generating novel hypotheses from literature review, designing experiments, scripting lab automation protocols for robotic execution, analyzing results, and producing draft papers with auto-generated peer review simulations. The AI Scientist framework demonstrated the first end-to-end autonomous scientific paper generation. And while the paper requires significant human editorial work to be publishable, the trajectory is clear. Science Agent Bench evaluates agents specifically on translating research paper tasks into executable code and figures, measuring where agents can operationalize scientific knowledge, not just recite it. LabBench targets biology-specific reasoning, where agents must reason over genetic sequences and design web lab experimental protocols that are physically executable. Multi-agent frameworks in healthcare combine isolated expert capabilities to achieve safer, more reliable diagnostic than generalist foundation models could accomplish alone. Agent Clinic simulates a virtual hospital where specialized diagnostic agents interact with patient data, medical imaging, and reference literature to generate diagnosis and treatment recommendations. EHR agent requires agents to reason over structured electronic health records alongside unstructured clinical notes, a genuine multimodal, multi-document reasoning task. Guard agent adds a dedicated privacy safety layer that monitors agent actions for HIPAA compliance and data exposure risk before execution. The critical design principle in medical AI is that the multi-agent architecture should allow domain experts to validate each specialist's contribution independently before the system synthesizes a recommendation, creating an auditable chain of reasoning that regulatory frameworks can evaluate. As missing modalities, video, audio, tactile inputs merge with extreme test time scaling and self-evolving memory systems, the industry broadly anticipates the emergence of highly powerful weakly general systems by late 2026 2027. These are not AGI in the philosophical sense. They are not universally competent across all domains, but they are systems that can autonomously undertake sustained multi-week research project, build and deploy a production software system from requirements, coordinate complex multi-party negotiations, and manage physical infrastructure. Capabilities that are economically indistinguishable from the labor they replace. But there are five critical gaps that must be closed to reach this horizon. They are personalization, long horizon interaction, world modeling, scalable multi agent training, and governance frameworks. Each gap is an active research frontier with concrete progress. The long term vision is not a single super intelligent model, but artificial collective intelligence, a robust, decentralized ecosystem of millions of highly specialized, persistently learning, networked expert agents, each expert in a narrow domain, all connected through A2A and MCP protocols, collectively exhibiting generalist capability through coordination. This mirrors how human civilization achieves collective intelligence, not through individual genius, but through specialization, accumulated institutional knowledge, and coordination mechanisms. The difference is that ACI operates at machine speed, with perfect memory and no communication friction. The challenge is the emergent behavior. When millions of autonomous agents interact persistently, what macro level intelligence arises? And how do you ensure it remains aligned with human values rather than optimizing for locally convenient proxy objectives? The culmination of agentic AI maturity model is ecosystem intelligence. Agents embedded as the operational intelligence layer connecting digital, physical, and ecological systems at planetary scale. Early deployments are already documented and live. In the Singapore Nanjing Eco High-Tech Island, the digital twin agents use real-time environmental sensing and adaptive regulation to shift urban governance from reactive maintenance to anticipatory autonomous climate resilience, managing ecological parameters across the entire island continuously. AI optimization models are deployed to manage nature-based carbon sequestration, processing terabytes of spatial data to generate actionable ecological blueprints for urban wetlands and rooftops, dynamically adjusting sequestration strategies based on real-time atmospheric and hydrological sensor networks. More advanced systems like intelligent bio-based green facades, integrating regenerative substrates, active soil life, and passive irrigation are being reconceptualized as AI-governed climate adaptive infrastructure, where agents monitor and optimize living biological processes in real time. Level 6 agents do not merely process information, they close feedback loops with the physical and biological world, exercising autonomous control over living systems at infrastructure scale, defining a new era of planetary scale technological symbiosis. Artificial intelligence has permanently evolved from a technology that provides answer into a systemic infrastructure that executes action. The agents are not coming, they are already operating. They are writing production code in real repositories. They are managing real customer relationships, running real scientific experiments, and making real procurement decisions. The technical vocabulary that we have built today, foundational reasoning, self-evolution, collective intelligence, in-context versus post-training optimization, is the precise language needed to design, evaluate, and govern these systems responsibly. The performance ceiling of agentic system is determined not primarily by which base model it uses, but by the quality of the reasoning infrastructure, the planning architecture, the memory system, the evaluation mechanism, and the governance constraint that surrounds the model.